The time response of a system to any input can be divided into two contributions: the transient response and the steady state. So, for example, if we have the output of a system, the response of a system to certain input, for example, like this function y of t, this signal, is the result of adding up two different signals. One is like this, and this is y t of t plus another signal, which in this case is constant, and this is yss of t. So y of t is equal to yt of t plus yss of t. Y of t is the transient response, and ss of t is the steady state. The transient response has the property that when t goes to infinity, it tends to 0. It decays. The limit of that part of the output when t goes to infinity is 0. So as time goes by, it tends to vanish. The steady state is simply what is left, what remains when the time tends to infinity. Well, obviously, if the input u of t keeps changing, it is very hard to distinguish what is transient and what is steady, because the input itself is not steady. This is why the concept only really makes sense for standard inputs like the step or the ramp or a sine wave, a sinusoidal function, all of which show certain kind of regularity. The mathematical justification of this differentiation comes from the calculation of the response of systems to all these functions. As we know, to calculate the output of a system described by its transfer function, we have to multiply the transfer function by the Laplace transform of the input u of s. And now we have to expand this into a sum of different, well, I'll just write y1 of s plus y2 of s plus all the different factors. Let's say yn of s. Now we can find y of t by inverse transforming each one of these factors. So here we would have y1 of t and so on and so forth. Now in some of these functions, and well, actually in many of them, certain exponential terms, such as for example e to the minus 5t, terms like this show up, and in them the exponent is closely related to the position of the poles of g of s in the complex plane. They could be here, they could be here, but these positions define the exponents in each one of those functions. Now, if the real exponents of e in all those functions are negative, then the terms in which they are included will eventually vanish, or at least they will tend to 0. They will tend to 0 here and here. Well, once all of them, all the real exponents in all these functions have decayed, we can say that the system is in steady state, and then y of t is almost the same thing as yss of t. Well, this is maybe not a very clear distinction between steady state and transient response, because the exponentials never really reach 0. But in practice, well, there's a moment in which we can assume that they are actually 0, and we can disregard their contribution. We use the parameter known as the settling time to differentiate when the transient response is still acting and when it has vanished. So for example, here we know that there's a point in which the response is inside certain bounds, and in that point, which we call TS, the settling time, from then on we can assume that this holds. But this is for the step response. In the case of other inputs, well, it may be tougher, but we can pretty much just by looking know when the transient response has disappeared. So in this ramp response, I would say this is the time in which there's only steady state, and in the case of the sine response, it is maybe even harder. So if we have this input, maybe we have to wait. Well, this is not regular at all. Okay, this is better. Maybe we have to wait a certain amount of cycles until we can find the steady state. So maybe the response is developing here, but from certain point like this, we can say that only the steady state is left. Now both transient response and steady state are equally important. The steady state allows us to analyze whether the final position of the system is good enough for our purposes. It can be associated somehow with accuracy. The accuracy of the system. For example, if we want to control the temperature of the room, of certain room, so if we are measuring the temperature here in the center of the room, maybe an error of 5 degrees in its control may be good enough for us, because, well, 5 degrees, it's comfortable enough, even if it's above or below our desires. So in this case, this error here of 5 degrees is good enough. But maybe if this is the temperature of some chemical process or biological process, or for example a manufacturing process, then maybe 5 degrees is completely wrong. It is a fatal error, and we need to make the system more accurate, closer to the reference, to what we want. So this is characterized through the steady state response. On the other hand, the transient response is telling us how the system goes from its initial state to the final one. Most of the time we not only want to end up in a good position like this, but we also want a fast and nice transition, like for example this one. So in the same example of the temperature, when we change the set point of the thermostat, when we switch it from 20 to 25 degrees, for example, it is not enough to know that we'll eventually reach the final temperature. We want it as soon as possible, and if it's possible, not by going up and down, not by freezing and then boiling and freezing again until we finally end up in 25 degrees.
And this is even more important, for example, in the cooling process of a nuclear plant. If we need to cool the the reactor, well, we need to act as fast as possible. The control system must respond as fast as possible, because otherwise, well, we all know what happens. So the purpose of our control designs will be to shape both the transient response, both yt of t, and the steady state yss of t, since specifications concerning both of them will be given to us.